Semiconductor manufacturing basics. To manufacture chips, the first step is producing silicon wafers. Melt sand at 1,800 degrees. Boron adjusts wafer conduction, heat, and insert seed crystal. When the seed contacts the hot liquid silicon, the surface temperature instantly drops. As it's continuously rotated, molten silicon adheres to and gradually solidifies. This produces an ultra-pure silicon. The ingot is then sliced into wafers thinner than 1 millimeter. Freshly cut wafers have rough surfaces, requiring polishing and other finishing. You obtain perfectly flat silicon wafer, being extremely delicate. Wafers need through oxide layer deposition. This requires oxidation. This is oxidation. Wafers are loaded 25 per, then transported into the oxidation chamber. Robotic arms position each wafer precisely. Oxidation then begins. First, oxygen is injected into heating coils maintain high temperature until reaching the threshold where oxygen reacts with silicon surfaces, forming insulating silicon dioxide. Next comes photolithography, the most challenging chip-making step. Photoresist coating precedes lithography. Finished wafers are transferred to coating equipment. Using centrifugal force from rotation, photoresist is evenly applied. After coating, the lithography process begins. This EUV lithography machine is among humanity's most complex inventions. It utilizes extreme ultraviolet UV, which narrows through multiple lens reflections. Before passing through the photomask, the photoresist on the bottom wafer, the photomask works similarly. To this ink, it's engraved with integrated circuit. When light passes through the photomask, it transfers the circuit patterns onto the photoresist. Under light exposure, chemicals in the photoresist begin react. Areas become soluble. Next comes the development process. The wafer is immersed in developer solution, washing away the soluble photoresist, while unexposed areas remain intact. However, after development, circuit patterns only exist in photoresist. How to etch circuits onto the silicon. This requires etching tech. The most common is dry etch. This is an etching machine. Place the developed wafer inside. Then, introduce carbon tetra as plasma into the etching chamber. The plasma reacts chemically with the wafer surface, while photoresist-covered areas remain unaffected. Thus, the mask patterns are etched onto the wafer, but in etched areas, the oxide layer gets removed. Solution. This calls for deposition technology. First, transfer the wafer to deposition equipment. Then introduce silane gas and apply plasma. Controlling reaction pressure causes hydrogen atoms to detach, leaving silicon atoms to deposit. After the reaction, a protective layer forms. Additionally, to enhance chip performance, ion implantation is required. Ions are accelerated by high-voltage field and implanted into the wafer, completing ion implant. Up to this point, we've built numerous structures on the wafer. How to interconnect them? Metal filling is needed. With billions of such structures require, the interior resembles a megacity. Actual chip manufacturing is far more complex than this, involves numerous all operations are performed at nanometer scale. These processes intersect and repeat, ultimately producing complete. Then the wafers are diced into individual, followed by packaging and testing. Chips that pass testing can be installed in electronic devices. Chip manufacturing basics. Packaging.
This is a completed wafer, with devices fabricated and wiring laid out. The small square grids visible are individual chips. But the chips we commonly see don't look like this, they look like this. Because those invisible to the naked, billions or even hundreds of billions of are all contained within such a casing. Without this protective shell, the chip would become extremely fragile. Don't underestimate this unassuming package. Actually, how to add protection to chips, or more professionally speaking, chip packaging, is itself a high-tech process. For a chip to function properly, it needs connection to external circuits. For example, this common connection method uses these metal pins that insert into PCB through hole to establish circuit connection. Internally, wires to the chip die. Chips packaged this way become a single chip may occupy significant PCB real estate, and because of internal wiring, the die casing needs substantial thickness. Modern electronic devices demand increasing, which raises packaging requirements. how to achieve simpler packaging structures, making chips more compact, occupying less PCBs. Now if we disassemble any smartphone, we can see this is what the chip inside a smartphone looks like. No visible pins can be seen at all. The chip connects to the circuit board. This is because these chips use more advanced and demanding ball grid array packaging. If you flip a chip over, on its underside, you'll see spherical metal solder bumps. These bumps connect the chip to the circuit. This packaging method not only allows chips to occupy less PCB space, but also simplifies their internal structure. No wires are needed to connect dies to solder points. Instead, directly connect to the die's internal structure. This significantly reduces internal making chips much thinner. Beyond structural in packaging technology, another technical challenge is selecting appropriate packaging materials. Stronger materials aren't always better. For appliances, AC units, TVs, and game consoles, where the environment is stable, even if chips fail, the consequences aren't severe. Thus, their packaging requirements are less stringent. These chips typically use special plastics to encapsulate the silicon die. This method is called plastic encapsulation, sometimes to reduce costs. A simple drop of glue suffices. Once dried, it counts as packaged. This is called glob top encapsulation. But sometimes, chips operate in harsh environments, or their failure could have serious consequences, like chips in automobiles or military applications, require much higher packaging standards. The most demanding are chips used in satellites and spacecraft. They must endure extreme temperatures and environments while constantly bombarded by cosmic rays. Therefore, for this type of chip, plastic encapsulation is often instead. More reliable metals or ceramics are chosen as chip. Packaging is also a crucial part of chip manufacturing, requiring profound technical and industrial expertise. China has already established certain competitive advantages in chip packaging. We have every reason to that in the foreseeable future, China's packaging technology will reach new heights, driving the vigorous development of the chip.